is going to be exploring multiferricity and high entropy RMnO3 with optical second harmonic generation. Just a reminder, if anybody who has come late, we have a timer for 12 minutes for your talk and then 3 minutes for questions. Please feel free to write your questions in the chat or raise your hand after to ask the speaker. So Graham, I'm going to hand it over to you. We can see your screen and hear you.
Okay. Thank you, Galen. Let's see. You can hear me, right? Okay, cool. Okay. Yeah, my name is Graham Lang. I'm from Virginia Tech, and this is my talk in looking at multiferroics with second harmonic generation. So usually I'm at Virginia Tech doing magneto-optics work with Giddy Cotoparast, TR-MOC type of stuff. But this summer I got to go to Penn State and participate in an REU. I got to work in Venkat Gopalan's group called Unlock and learn second harmonic generation, which is their bread and butter sort of technique for characterizing materials, particularly ferroelectrics. And I want to give a quick shout out to my grad student mentor, Akash Saha, for guiding me through this project. So a multiferroic, if you're not familiar, is a material where you have both polar and magnetic order. So ideally something that is both ferroelectric and ferromagnetic. And a ferroelectric is just like a ferromagnet, but for the electric polarization. The interesting thing, the exciting thing about these materials is that these two order parameters may be coupled. So you could, in principle, construct a device where you control the magnetization with electric field. And this fits into the meso architecture that I'm sure somebody else at this talk has mentioned, or at this conference. But these multiferroics exist, but there's limitations on making them useful for device applications. They're in general pretty hard to find because the polar and magnetic order sort of want different things. And the ones that do exist, they typically have low transition temperatures, especially for the magnetic phase. And that magnetic phase is often anti-ferromagnetic or weak ferromagnetic. So we want to engineer materials that improve these properties. The materials that I am interested in are these rare earth manganites that have this standard perovskite stoichiometry, hexagonal perovskite structure. They're ferroelectric at room temperature and anti-ferromagnetic below about 70 Kelvin. So I'm going to talk more about some of just the background properties of these manganites. So at room temperature, below 1000 Kelvin, you cool down from this 6 by mm phase. You break this mirror plane perpendicular to the Z3 axis. And the displacement of these rare earth ions gives you your ferroelectric polarization. And you have space group P6-3CM and point group 6mm. These are also anti-ferromagnetic. So when we talk about magnetic symmetry, we use the magnetic point group. And we include time reversal as a symmetry operator. If time reversal exists in the magnetic point group by itself, so 6mm1' for the paramagnetic phase, this means the material is not magnetically ordered. You apply time reversal symmetry, and this basically kills all the spins of manganese ions. But below the anneal temperature, you kill this time reversal symmetry operator, and you can have subgroups of this 6mm1'. So you still may have time reversal symmetry tied to one of the individual symmetry operations. And this gives you the different magnetic structures that you can have. And you may have transitions between these structures, spin rearrangements, once you're below the anneal temperature. So for example, I believe for yttrium manganite, you start in 6' mm', at 70 Kelvin, and then somewhere around 4 Kelvin or a high magnetic field, you transition to the 6 M' point group through this anti-phase spin rotation. So this is the kind of thing that we are looking to see in these manganites. So the material that I got to work on is this high entropy manganite, where you have 6 different rare earth elements all in equal concentration in the R site. These high entropy materials are sort of a new thing, and they're not super well understood, but people have been getting good results with them. The general principle is that if you crank up the S delta T term in your Gibbs free energy, this can counterbalance a higher delta H, and you can stabilize different phases than you would be able to otherwise. And people have had success with this in multiferroics, for example, in rare earth ferrites. So our collaborators in Dr. Maria's group synthesized thin films of these. They did XRD, and confirm this is space group P63CM. So this is hexagonal like we expect, and the PE, the PE measurements, ferroelectric characterization is rather promising because we have high remnant polarization to microcoulomb per centimeter squared. And these are insulating, where most ferroelectrics tend to be fairly leaky. So our job, my job with AtC-AtG, is to go in and confirm that the AtC-AtG still reflects the 6 mm point group, that this matches up with the X-ray diffraction, because you could also get an orthorhombic phase and then cool down and look for phase transitions, particularly magnetic ones. So second harmonic generation, some background on this. Linear optical effects, right? You hit your crystal with light of some frequency, and if the electric field is small enough, the restoring force is linear, you radiate light at the same frequency. If you crank up the intensity of the electric field, you can reveal higher order terms of this potential, and you can get, frequency mixing, harmonic generation, all kinds of good stuff. Second harmonic generation is the simplest of these effects. So you absorb 2 photons, you emit a photon at twice the energy. And the reason this is such a useful characterization technique is it gives you access to a third-rank polar tensor, which is very sensitive to inversion symmetry breaking. So people have been using this for a while to characterize ferroelectric materials because you need to break this inversion center to have ferroelectricity. And it is mechanically much simpler than something with XRD, so it's easier to do in situ and look for phase transitions and things like that. Now, the one slightly different thing with AtC-AtG about this project is we're also looking for this time-odd component to the second harmonic generation. So this is a bit separate from what people typically do in characterizing ferroelectrics. This polar component of the AtC-AtG is time even. It ignores any magnetic symmetry, the magnetic point group. But once you break your time reversal symmetry, you can have this time-odd component that reverses sign under time reversal, and it will have different selection rules. So this you can use to identify your spin structures in an antiferromagnet, for example. And Manfred Fiebig, in his work, essentially pioneered this technique, looking at rare earth manganites and chromium oxide, stuff like that. But experimentally, how we do this is fairly simple. We have a 100 nanometer pulsed laser polarized at angle 5. We hit our sample and we collect the second harmonic light polarized along either the X or the Y direction, and then we sweep our incident polarization while measuring intensity. And that's what gives us these polar plots. So this right here is just a theoretical calculation. I go in and I apply the symmetry operations of the 6 mm point group, so the 6-fold axis of these 2 mirror planes. And it gives me selection rules on my tensor that give me this unique polarimetry, so I can know what to expect. And then here we have the actual measurements at room temperature to confirm that this is 6 mm and not orthorhombic. So we have the expected polarimetry at oblique incidence, and we have to do some other checks to rule out other point groups, so no signal at normal incidence, and the polarimetry does not change if we tilt the sample. And these are things you can verify if you play around with the tensor transformations. Okay, but this is the interesting bit. What happens when we cool down? We do see a phase transition around 275 Kelvin. We see a symmetry breaking. These 2 lobes in the Y polarization shrink, and this indicates that we've broken the mirror planes perpendicular to the Z1 and Z2 axes. Now, what is responsible for this could be a structural transition, so something in the polar AtC-AtG, where you literally break these mirror planes, or a symmetry breaking in the magnetic phase transition. So you can have a few different point groups. And we are also checking a normal incidence to rule out other possible transitions. We have the X polarized intensity as a function of temperature too. This unfortunately doesn't tell us much because the spreading out of the polarimetry is not exclusive to the phase transition. And we can also plot our new tensor component that emerges below the phase transition as a function of temperature, and we see it saturate. So I want to quickly clarify the difficulty with the magnetic AtC-AtG. Fiebig in his papers emphasizes that you need the spectroscopy degree of freedom to do this reliably. And we did not have the equipment for this, the setup for this. We were hoping to avoid that because we expected a different point group that wouldn't conflict with the existing polar SHG signal, but you can see for the polarimetry we observe, there's a few different combinations of crystallographic and magnetic point group you can have that when you add them together, they overlap and they give the same tensor. And by the way, this is the Voigt notation. So the third rank tensor is reduced to the 3x6 matrix using its intrinsic permutation symmetry. But to sum things up, we've confirmed that the SHG reflects the 6mm point group. So that is in order. And we have a phase transition just below room temperature that may be structural or magnetic. Now, the magnetic possibility would be exciting because this is very high temperature, but that's also the reason it's more unlikely. Our collaborators have also tried SQUID, although they were not very confident in their results, and they found it to be very weakly paramagnetic. So it's doubtful, but still possible if we were to look at it again. And the structural transition to 6 is not something that has been reported in these magonites before, to my knowledge. It could be a result of the high entropy formulation. It could also be something exclusive to thin films because most of the literature is on single crystals. But one of the main things we've also learned is we definitely need the spectroscopy degree of freedom to separate the magnetic and polar SHG contributions. But in the future, there is, of course, investigating this phase transition and nailing down which point group we transition to. And also potential extensions, checking out how the lattice strain affects the symmetry of the crystal, like getting different phase transitions for different substrates, because there have been some neat papers published on strain engineering in these magonites, coaxing out net ferromagnetism out of the orthorhombic phase. But that concludes my talk.
All right. Thank you very much, Graham, for this very nice talk. So yeah, the floor is now open for questions, and I have some questions in the chat. So I see Kawar Ismail, you have some questions. If you'd like to unmute, you can ask them now.
Oh,
Thank
yeah,
you.
wait, sorry. Oh, go ahead.
Yes, thank you so much, respected professor. You can present second harmonic response of magnetic response of materials. I just ask a simple question: how can you compare with a linear magnetic response with the third? You can study the second order or maybe third order. Can you explain something?
So this is a second. Okay, so to clarify where the
Yes,
magnetic SHG is
this
coming
is the
from,
second order. Yes, I know.
it is
This
second
is the
order.
second order. But you can compute some linear response. How can you compare linear with the second order magnetic moments?
In terms of linear magnetic effects, like getting a polarization that having a, are you saying you would have a second rank tensor for the linear effect that depends on the magnetic symmetry? Or
Yes, I know. I know central symmetric. Yes, for this non-linear, we need unsymmetric materials. Yes, I know. And this,
Okay, I'm just saying I don't know. I haven't heard much about linear effects relating to the magnetic symmetry.
No, I just put a request about like here the polarization chi1 and polarization chi2 and polarization chi3 orders. It's like how can this magnetic moments is changed order 2i's or maybe order 3, like just in case of linear optic, if we can talk about optics, linear optics, then the refractive index become 2, for chi2, and chi3 the refractive index become 3. Similarly, if we can ask just similar, we can discuss this thinking non-linear response of magnetic properties of materials. Maybe material is hexagonal or unsymmetric material. Then these have some linear or non-linear effect, like some ordering, twice, third orders, and fourth orders.
Mm-hmm. So the way that we are using this to look at the symmetry of the material is by imposing selection rules on the tensor. So really, it's a question of like, can you find a tensor that is sensitive to the symmetry breaking you want to look for? And it happens to be this particular second order effect happens to be useful for that. Finding the ones that also respect the magnetic symmetry is a bit trickier. And of course, you can have magnetic dipole contributions to SHG, which are much weaker. This is not that. This is a bit more curious because this time odd component actually comes from what is it called? The Ginzburg-Landau functional theory of phase transitions formalism. And the reason this component is time odd is because it's a product of a 6-rank axial time even tensor and the antiferromagnetic order parameter, which is time odd and axial. So this gives you a time odd polar 3rd-rank tensor. And if you really want to go in and figure out where you can find optical effects where you will have magnetic symmetry, I think that is the way you would do it. I don't understand it super well, though.
Yes, I also perform some linear, nonlinear response of optical response. So that's why I ask about question, because you perform some magnetic and magnetic properties change with orders, go higher orders. Just a humble request.
Oh yeah, I mean, of course you could have higher order effects. I believe, yeah, I haven't read into them myself, but
if I put a request,
Sorry
can
to interrupt
I
here,
get this
guys.
lectures or not? Can I get this slides or not?
oh, I can send you the slides, yeah, if I can get your email.
Yes, thank you so much. I write my email. Thank you so much.
Thanks.
Great.